So here is an argument represented in the language of sentential logic, so what we call a sequent. Sorry, I hadn't put in the conclusion. So we have a first premise here, then the comma separates that from the second premise, that comma separates that from the third premise. Here's the turnstile, the conclusion indicator, and then there's our conclusion. And we can identify what kinds of sentences these are. This is a disjunction, this is a conjunction, and this is a conjunction, and so is the conclusion. And the first premise says either A or either B or C. So for that to be true, at least one of these sentences, A, B or C, must be true. If A is true, it'll be true because it has a left disjunct. If A is false, then this disjunction that makes the right disjunct has to be true, and for that to be true, either B has to be true or C true. So at least one of A, B and C must be true if this premise is true. They could all three be true, or two of them, but at least one of them must be. Second premise is a conjunction. For it to be true, both its conjuncts must be true, and both its conjuncts are conditionals. The third premise is also a conjunction. Same thing applies. Its left conjunct must be true. That's a negation, its left conjunct. So to get true for this conjunct, we must have false for what's being negated inside the parentheses. And then this will have to be true. The conclusion is a conjunction too. That will be false just so long as at least one of the conjuncts is false. We have 1, 2, 3, 4, 5, 6 atomic sentences. So the complete table will be 2 to the power 6, which is 64 lines. So 64 lines this way, 1, 2, 3 premises and the conclusion, so a number of columns too, so a big table. Is this sequent valid? Well, we could do the whole table and then go through it line by line and see whether there's a line on which the premises are true and the conclusion false. Or we can use the method where we search for an invalidating assignment. And if we find one, then we know the sequence is invalid. So let's try that. So we have A, B, C, D, E, and F. And we want to see if there's an assignment to these on which we get true for the first premise, true for the second premise, true for the third premise, and false for the conclusion. And as always, we start where we have the least choice. Having no choice is good in this sense. So, well, as I said, there's three ways, at least three ways this could be true. A could be true, or B could be true, or C could be true. And actually there are more ways than that. A and B could be true, A, B and C could be true, B and so on. So there's a sort of lot of ways of making the first premise true. So we haven't too much choice there. With the second premise, it's a conjunction, so its conjunct must be true. But there are three ways to make conditionals true, so we still have lots of choice there. But when we come to the third premise, we don't really have any choice. The left conjunct must be true to make the conjunction true, and so must the right conjunct. And the right conjunct is F, and so we can already write in a T for F. And so we can also put that T for F into the conclusion. And now, we have no choice in two places. Let's look at this one. So in order to have true under the negation, we must have false for what is being negated. So what's inside the parentheses must be false in order for its negation to be true. And there's only one way to make a disjunction false. That's by making both disjuncts false. So D and E are false. And we can take those then and put them into here. And now, for this conjunction to be true, its left conjunct, the conditional, if A then D, must be true. But if D is false, if A were true, this would be false, because a conditional is false when its antecedent is true and its consequent is false. So we can't put true here, because then we have to make this F. So we have to put false here. And the same reasoning applies here. If B then E, but E is false. If B were true, we'd get false here, so B must be. Now if we take those two truth values, A must be false and B must be false, right? So if we take those two truth values and put them in the first premise, well, now the disjunction has a false left disjunct, so it must have a true right disjunct, or it wouldn't be true. And because the left disjunct of that disjunction is false, we must make C true, right? And now when we go and take that truth value and put it in the conclusion ends up true. And we failed. We have failed to find an assignment of truth values to A, B, C, D, E, and F that gives us true here for the first premise, true here for the second premise, true here for the third premise, and yet we don't get false for the conclusion. And so this is a valid sequence. It's not possible for the premises to be true while the conclusion is false. And in a sense, this shows the invalidity of the argument. But we have, of course, to be confident that we haven't made a mistake doing this. And also, this method doesn't capture anything of the way that we think about valid arguments. So let me just talk you through this argument. The first premise says either A or B or C is true, so at least one of them has to be true. The second premise says if A is true, D is true, and also if B is true, E is true. So if either A or B were true, then either D or E would be true. But the left conjunct of the third premise says neither D nor E is true. So if D is false, A can't be true. And if E is false, B can't be true. And so, for the first premise to be true, C must be true. Right? A can't be true, because if A were true, D would be true. But the third premise tells us D is false. And if B were true, E would be true. But the third premise tells us E is false. And so neither A nor B can be true. And so if the first premise is true, it must be C that's true. And then for the third premise to be true, F must also be true. And so both C and F must be true. And there what I've done is reason through in a series of steps to the conclusion that both C and F must be true, because, well, F must be true if the third premise is true, and if the first premise is true, it can't be true because A is true, and it can't be true because B is true, because if A was true, D would be true, but it isn't. And if B were true, E would be true, but it isn't. And so it must be C that makes the first premise true, and so C and F must be true. And the reasoning that I've done there involves several different kinds of inferences. For example, this one, if A is true, D is true, but D is not true, so A can't be true. That's a kind of inference that we call modus tollens in logic. And actually in the system we're using, modus tollens is not one of the primitive rules of our proof system, but a so-called derived rule. And that's something we'll get to later. The same reasoning for B, right? If B were true, E would be true, but E is not true, so B can't be true. Modus tollens again. Then, if neither A nor B can be true, if they're both false, C must be true. That's a piece of reasoning that we call disjunctive syllogism, or in the system we're using it's called wedge elimination, but these names are. And then of course, if C has to be true to make the first premise true, given that A and B can't be true, and F has to be true for the third premise to be true, then both C and F must be true. And the reasoning that's involved there is essentially a series of truth-preserving steps. We assume the premises are true, and in a series of truth-preserving steps, we get to the conclusion, both C and F, in a series of truth-preserving steps from the premises. And this is the nature of the proofs that we do in sentential logic. Let me just then show you how we set up the proof. I'm not going to do the proof because we have to learn the rules for each of the kinds of sentences that we have. But the structure of the proof looks like this. At the top, we write out our premises. Either A is true, or either B or C is true. Here's the second premise. If A, then D, and if B, then E. And here's the third premise. Neither D nor E, and F. And those are the three premises of the argument, and we just number the lines on which they're written. So we write one premise per line. Then the bottom of the proof, the last line of the proof, we don't know what number it will have because we don't know how many steps we'll have to take to fill in this gap. But on the last line of the proof is the conclusion. Now, these premises are just assumptions that we're making. We begin by assuming the premises are true. And so over here we write A, which stands for assumption. Am I saying this is true? No, I'm assuming it's true. Over here, we keep track of the assumptions we're making. So, in this case, we number each assumption by the line number on which the assumption is made. It's a bit hard to understand why we do this until we start doing the proofs. And then the idea is that on line 4, we will apply a rule, a truth-preserving rule, to one of the sentences on 1, 2, or 3, or maybe to 2 of them. And here we will write a different sentence which has been derived, has been proved from earlier lines in the proof, lines above it, by a truth-preserving rule. And I'll give you one example of a truth-preserving rule here, which is that if a conjunction is true, then its left conjunct must be true. And if a conjunction is true, then its right conjunct must be true. This is the rule that in our system is called ampersand elimination. That's not a name I like particularly, but that's the name they give it. So for example, on line 4, we could write neither D nor E, and over here we would say 3 ampersand elimination, because the sentence on line 4 has come from the sentence on line 3 using the truth-preserving rule ampersand elimination. And here we note the assumption on which the sentence on 4 rests, which is 3, which is an assumption. We can do the same thing on line 5 with the other conjunct, F. That would also be 3 ampersand elimination, but this time taking the right conjunct. And it's clear that we need 5, F, because that's going to go into our conclusion at the end. So the structure of a proof is basically assume your premises at the top, write your conclusion at the bottom, fill in the gap. Fill in the gap with truth-preserving steps, always deriving the new sentence or the different sentence from the sentences above it in the proof. So on line 5 we can cite line 3, but on line 5 we can't cite line 6. In that sense, everything comes from the assumptions at the top in a series of truth-preserving steps until we get to the conclusion. Why does this prove that the sequence is valid? Because validity, remember, is that if all the premises are true, then the conclusion must be true. So what we do is we assume the premises are true, and we show from those premises alone, so all that can be in the assumption set for our conclusion are the premises we assumed at the beginning. And that's the next thing that we're going to do. We're going to learn the truth-preserving rules by which we prove the conclusion of a valid sequence on the assumption that the premises are true.